Welcome to Lesson 4 of 11 Things About Data. I'm Alistair Kroll, Chair of Forward 50, and I've put together these 11 lessons to help you think and function in a data-driven world. Now we're going to look at stats, queries, and how to explore data. And don't worry, I'm not going to start teaching you stats, but we are going to talk a little bit about what data is. Simplest way to think about data is just tables with structure. If you've ever used a spreadsheet or looked at a table, you're working with data. In this case, I've got 4 different fields: first name, last name, Medicare number, and province. Obviously, these are all made up. And I've got 4 rows here representing 4 different records in that data. When you talk about columns of data, we're talking about the fields. When you talk about records, you're talking about the rows. So data is generally tables with structure like this. And already you can see there are some challenges here because the Medicare numbers might be different, but also things like, is Leguin someone's maiden name because they're in Quebec and they didn't get, or is it their spouse's name because they moved there? So already data can be very complicated. And it gets worse. Sometimes data is just a set of key value pairs, a label, and then the value. So name is Jane Doe, age is 26. Sometimes the data is missing, so employer is not available. Sometimes the data contains multiple fields, so 2 languages spoken. So data can be very complicated. And every time you start to think about data and it seems confusing, just remember that at its root, it's a bunch of facts like this we're just trying to make sense of. In the same way you would sort a spreadsheet or you would ask a question of something, it just happens to be stored in very powerful systems that can move millions of things around in a split second. Now, these little facts about data are very trivial. They're not really related. One of the great breakthroughs in data in the past 50 years was the invention of what's called a relational database model. Instead of just having a bunch of rows of data, we now had information that was related to other pieces of information. So for example, I might have a school address, and there's many teachers at that school and many students at that school. And each student might have one parent who was the contact. And so we started to see these relations where I could go into the teacher record and change which school that teacher was at. Or I could say, show me all the teachers at this school, or show me all the students at the school. These relationships tied together several tables. In the earlier example, when you saw Medicare numbers, I might have another table that talks about all the procedures done by a hospital. And there might be a medical record that has the Medicare number for that procedure. So now I could say, show me all the medical procedure Alistair's had done, or I could say, show me all the procedures done by this hospital and all the patients. That's what really opened up the world of data, was going from these flat records to relational records. Now, you might think that data analysis is what takes up most of the time, but it's not. 80% of the work in analyzing data is cleaning things up. Sometimes there's data that's missing. Sometimes there's stuff that's wrong. Sometimes it's misspelled. So you think that it's 2 values, but it's actually the same one. Sometimes the date format is different. Sometimes they're using a different currency. Sometimes some things depend on others. Sometimes 2 people have the same value, so it looks like they're the same person. Most companies estimate that 80% of the work of processing data is what's called ETL. ETL stands for extract, transform, and load, but that's just a really complicated way of saying take the data, clean it up, and store it somewhere. Generally, when you've got data like this, the first thing you want to do is to analyze it using statistics. You're going to say, look up the data and tell me, what's the average or what's the most common value, which is deadly because it turns out that statistics are very misleading. What I've got here is 4 data sets. These are called Anscombe's quartets. These are 4 data sets. Each of them has 11 points. They're clearly very different. The one on the bottom left is 4 things in a straight line. The one on the top right's a curve. The one on the bottom right has almost all identical values of 8 and then one that's very different. What's weird about this is that these all have the same average value. The average value for all of these is 9. If I were to look at the values of all of the dots that are here, the average on X, which is the bottom line here, is all 9. Clearly they look different. Imagine these are students. So in the bottom right corner, you probably have a bunch of 8-year-old students in a class and 1 older person visiting. So the average age of the class is 9. That's kind of misleading. The average of the Y value, which is the other axis here, is 7.5. It's not just the averages. There's a strong correlation between X and Y in both of these cases. They all give you the same blue line. So if you were trying to make a prediction, you would make the same prediction for all 4 of these. Notice I haven't talked to you about stats yet. I'm just saying that if you look at this data, this is very misleading. The actual data is very different. The variance, which is how much the things change, varies in the same way by both dimensions. Now, what this means is that just because someone's brought you data like the averages, you need to think about what's actually going on. And one way to do that is to visualize the data, which is the point of Anscombe's quartet. But imagine you have a question. You want to know what's causing traffic accidents because you'd like to stop traffic accidents from happening. So you go and get some data that says, oh, look, most traffic accidents happen within 30 kilometers of a person's home. Okay, so the conclusion is people are careless when they're home. It's familiar surroundings, so we probably should give them more lessons or be more careful driving near home. But then it turns out that that data is based on accidents over time. And guess what? Most people spend most of their time near home. So the data is actually kind of misleading. So then if you said, well, how about accidents over miles being driven? Well, it turns out that you have more accidents in urban areas by suburban drivers. People from the suburbs go downtown and they have accidents. Why is that? Is it because they're not familiar with the environment? Or is it because there are more traffic interactions in a dense environment, more traffic lights, you're passing cars more, you're turning, you're merging? And what data would you need to collect that information? And then you might say, okay, what I'd like to know is how many driving events does someone encounter? And which of those events causes a problem, right? How many times does a person who's driving past somebody stop at a traffic light, turn an intersection, come near a school crossing, and so on? And then how do you get that data? And now you're ready to start analyzing the data. You have to go through this thought process before you start exploring it to understand the real question, not just the question. There was a great example recently of this in government, where instead of saying how many people are getting food subsidies and food checks, the metric should be how many people who are eligible for food stamps were unable to claim them. Because if the goal of a food stamps program is to help the most vulnerable, surely the most vulnerable are those who are entitled to them but unable to claim them because of technical problems, because of other access to systems, because of awareness or understanding. And so a more meaningful metric, if you want to drive the performance of food subsidies home, is to focus on how many people are unable to claim them and wrongfully turned away from those problems. So anytime you're doing data exploration, you start by asking a good question, and then you try and collect some of the data. And then you got to clean that data up, which often involves sorting it by each category, sort by country, sort by city, see if there's any outliers or any mistakes in there, fix those things, and then go back around this cycle over and over again until the data is relatively clean. This is a tiring process. There are tools that help with this stuff. Many of them use algorithms and machine learning. Once you're confident that your data is reasonably solid, you summarize that data. You start to say, hey, this is the averages, this is the ranges. You start to get the statistical stuff and you say, what's the baseline? What's normal look like? What does the past say? How has this changed over time? And then you start to compare it. What's related to this information? And finally, you can ask what's missing? What don't I have in this data set? And go back to asking the good question. And this is a constant process. The reality is that data is an ongoing conversation between the person analyzing it and the information behind it. Of course, you don't know how dirty that data is until you start cleaning it. So it's very hard to come up with a reliable estimate for cleaning data. And you can't tell whether you have the right question up front until you try and answer it. And so as a manager, you need to have very different expectations for how long it will take to work through data, because you don't know how messy it is, or if you're even asking the right question until you start to dig in. Now, we're going to get into some really interesting stuff about data and privacy in the next lesson, but hopefully that gave you a quick tour of stats and how to explore information.